My name is Declan Revenue. Thank you for taking interest in my poster, evaluating GCMS and LC tandem MS efficacy for characterization of a developed organic gunshot residue standard. To begin, I want to provide a brief background on the study. When discharging a firearm, organic gunshot residues are deposited on nearby surfaces. OGSR consists of stabilizers, plasticizers, and explosives found in ammunition propellant. For gun-related incidents, GSR is exceptionally useful in crime scene reconstructions. Therefore, investigating post-deposition trends can further the understanding of these traces while improving collection methods. This study sought to validate an OGSR standard of known concentration that can be applied to future transfer and persistence studies, functioning as a ground truth. The OGSR standard was evaluated using gas chromatography mass spectrometry and liquid chromatography tandem mass spectrometry. Additionally, the standard stability and storage was evaluated using two different solvents, acetone and ethanol. This study also addresses two research needs identified by the NIST OSEC GSR group, investigating persistence secondary transfer characteristics and compatibility with existing forensic laboratory instrumentation. Validating a reliable OGSR standard can improve the conclusions drawn from transfer and persistence studies. Also, in current literature, OGSR studies focus on LC analysis, narrowing the field's knowledge about instrumentation applicability. In compliance with Eurochem guidelines, the GC method validation was performed over 5 days with 3 injections at each concentration level. 8 of the most commonly studied OGSR compounds were selected to represent authentic firing events, which are seen on screen. 3 working stock solutions were used to prepare the calibration curve samples and spiked with deuterated diphenylamine as an internal standard. For GC, a 10-point calibration curve was constructed ranged from 0 to 3000 ppb, and for LC, the calibration curve ranged from 0 to 200 ppb across 9 different points, highlighted in Table 1. Following a trueness and precision assessment, the limits of detection and quantification, linear dynamic ranges, R-squared values, and other figures of merit were calculated. A similar procedure was followed for the standard stability study. Working stock solutions of the OGSR compounds at a concentration of 1000 ppb were prepared in acetone and ethanol instead of methanol. They were sampled 3 times over a duration of 1 week. When preparing these samples, the acetone and ethanol standards were pipetted into their respective vials and dried down using nitrogen gas. Following the dry down, the vials were reconstituted in methanol since this is a more suitable solvent for the GC and LC instrumentation. Samples for GC and LC analysis were reconstituted to 1100 ppb respectively. After analysis, solvent effects and stability of the standard were assessed using statistical tests including box plots and one-way ANOVA. As for the validation portion of the study, excellent linear dynamic ranges were achieved for both techniques with R-squared values exceeding 0.99 for all compounds. An example is depicted in the calibration curves for methyl centralite in Figure 3. Residual plots were also used to evaluate linearity. Table 2 portrays the figures of merit obtained from the GC validation performed in the study, alongside the LC figures of merit sourced from Feeney et al. LC is largely superior to GC, especially evident in the lower LODs and LOQs, except for nitroglycerin and 2,4-dinitrotoluene, which cannot be detected by LC with the used ESI setup. This is expected since LC is a more sensitive technique than GC. In Figures 4 and 5, the total ion chromatograms for the OGSR standard are shown. Each peak represents the elution of an OGSR compound due to the instrument separation techniques. Note the shorter retention times of LC compared to GC in Table 3, where the longest retention time for GC is 12 minutes versus 4 minutes for LC. However, retention indices can be calculated for GC methods, which function as a way of comparing results across various instruments and laboratories. For the solvent effects, acetone demonstrated slightly higher OGSR recoveries when used as a storage solvent as depicted in Table 4. The box plots in Figure 6 represent the concentration responses for acetone versus ethanol across the 3 days, 9 injections total. The left plot corresponds to GC's performance, which is closer to the spiked concentrations than LC's performance on the right. Figure 7 depicts ANOVA comparisons of methyl centralite stability across the 3 days. The absence of overlapping circles in the Tukey Cramer test indicates that there are statistically significant differences between the mean responses of each day. The standard stabilities and recoveries were not ideal. It is hypothesized that there are unaccounted factors in sample preparation that are influencing these results, since similar losses in percent recovery seen for both GC and LC. In response, potential factors that may impact recoveries were identified. These include the storage container seal, room temperature equilibration time, dry down volume, sample constitution, and headspace of the stock solution. A ruggedness test in the form of Plackett-Berman design will be performed to assess these factors' influences on the recovery. Those with the highest determined effects will be controlled. Method performance and sample response will be evaluated in future optimization studies. From the study, it is evident that the developed OGSR standard represents typical compounds found in OGSR deposits after a firing event. Therefore, this standard can be adapted to transfer and persistence studies. Overall, LC proved to be more effective at detecting and quantifying the OGSR standard. However, GC is better suited for analyzing some OGSR compounds such as nitroglycerin and 2,4-dinitrotoluene. As for the solvent effects study, acetone demonstrated better or equal recoveries of OGSR compounds. However, recoveries and stability of the standard were not as expected and will be evaluated in future steps of the study. Moving forward, future efforts will feature a ruggedness test for sample preparation to enhance sample stability and concentration recovery. Furthermore, the standard's recovery rates, when applied to different surfaces such as skin, clothing, and furniture, will be explored. Use of the OGSR standard in future transfer and persistence studies will allow for concrete conclusions about the mechanisms of transfer and behavior of OGSR. The authors would like to thank the NIJ for funding this project, and the opinions, findings, and conclusions are those of the authors and do not necessarily reflect those of the Department of Justice. Thank you.